Hi, I'm Ward Howard from the University of North Carolina, Chapel Hill. I'm a third-year grad student, well, actually fourth year now, and I'm excited to be with you here and to share about the Evryscope detection of the first Proxima Superflare and the impacts on Proxima's habitability and atmosphere. So, in 2016, a 1.3 or greater Earth mass planet was detected using the radial velocity technique around the nearest star, a common M dwarf named Proxima Centauri. Proxima Centauri, as I mentioned, is detected with radial velocities, which means you see the regular red shifting and blue shifting of the host star as the planet tugs on it in its orbit along its phase, which in this case is an 11.2-day orbit, as you can see from this sinusoid. And it was discovered using the HARP spectrograph Pale Red Dot campaign and earlier instruments from the UV's survey. So we have Proxima b now, and I'd like to draw your attention to two facts about this planet. One is that it's the best opportunity to characterize a potentially Earth-like exoplanet, and two, it's an extremely active flare star. So what effect would these flares have on the habitability of Proxima b? Do superflares destroy the exoplanet atmosphere? We know that UV flux from solar flares and from coronal mass ejections can destroy the ozone in an exoplanet's atmosphere. And we also know that without ozone, lethal amounts of UV radiation can reach the surface of the planet during superflares or events of 10 to the 33 erg or greater. It turns out that single superflares in CMEs per year do not necessarily deplete an ozone layer in a planet's atmosphere, but that multiple superflares in CMEs per year can indeed deplete the ozone in an Earth-like planet's atmosphere. But no one had seen a superflare on Proxima Centauri until now. In 2016, during the HARP's Pale Red Dot campaign, our instrument, the Evryscope, was also observing Proxima, and we observed a superflare of 10 to the 33.5 erg that was about 10 times larger than any flare seen from the star in any wavelength, with the next largest being an X-ray flare from 2004. And that's bolometric, that's total energy. And so you can see along the time series of our flare in minutes, from the flare peak, the normalized flux of the star, also displayed as inset images in the Evryscope along the top. We have the star in quiescence rising up to peak brightness, and then back down to quiescence again. At peak brightness, it attained about 40 times the quiescent flux in the camera exposure, which would have been about 70 times at the time scale of the human eye. So we've got this superflare, and it was detected by an Evryscope. But what is an Evryscope? Well, this is an Evryscope. The Evryscope, or wide seer in the Greek, stands for a 24 61 millimeter telescope system, and it's the first gigapixel all-sky survey. That's an enormous étendue. It's 13 arcsecond per pixel resolution and an 8,000 square degree field of view, and the Evryscope is capable of long-term, high-cadence monitoring of 15 million stars simultaneously. This is one Evryscope image of the night sky. It's a lot of stars. This is 1% of an Evryscope image. It's still a lot of stars. So let's just focus on one star for the moment, on Proxima Centauri. This is the Evryscope light curve of Proxima Centauri, which is just the brightness of the star versus time, where the time is just in days, and the brightness is in stellar absolute magnitudes in Sloan G. You can see our superflare event detected in 2016, as well as a number of other large flares that we observed. And in total, we observed 24 large flares between January of 2016 to March of 2018. So we want to know, how often do superflares like this occur, and what do they do to Proxima b's atmosphere? We can start to get at that information by building a flare frequency distribution from all of these flares, like this. This is kind of a complicated plot, so I'll break it down a bit for you. This is the logarithm of the total energy of the flare in erg on the x-axis, and this is how often a flare of that energy or greater occurs per day on the y-axis, and then we can fit a simple power law to that, along with posterior draws, to determine how often superflares occur. So the way this graph works is that a flare of 10 to the 32 erg or greater in energy occurs about once every 10 days. As you'll notice, our superflare is actually above this distribution, which means we either got statistically lucky and we normally would have had to observe longer to observe this same event, or that the power law changes at these ridiculously high energies, an order of magnitude higher than anything that had been observed before. I tend to favor the statistical argument, one, because we've actually observed more data since I made this plot and it moves down. So I think we just got lucky. But it is interesting to think about ways that power laws like this may change as a function of energy. All of these blue events were observed with the Evryscope, and they're just the flares from the previous graph. These yellow flares were actually lower energy flares observed on roughly a 40-day time series obtained by the MOST satellite in 2016 and were reported in a paper by Davenport et al. In 2016. So now that we have an answer that our flare frequency distribution says that 2 to 5 superflares should occur per year, what can we do with that information? Well, we can actually do a lot with it, but for right now, we're going to focus on habitability. So if I take that sequence of flares and I take that flare frequency distribution and populate out a 5-year sequence of flares and plug that into a climate model, what will that do to Proxima B's atmosphere? So we can take that and we can actually measure a 90% ozone loss in 5 years. And if you assume these same rates, that would be essentially complete loss on geologically short timescales. Now, as a quick reminder of how some of these processes work, I will point you to my wildly simplistic cartoon on the left-hand side, in which ozone is destroyed during a superflare. When a coronal mass ejection that sometimes is associated with a flare has a proton hit a nitrogen molecule in the upper atmosphere, it will often dissociate that nitrogen molecule, and the nitrogen atoms can then combine with oxygen to create a nitrogen oxide and a free oxygen. And then the nitrogen oxide can combine with an ozone to create another nitrogen oxide, and recombine to create a second ozone molecule. Now, there are other processes also happening during this whole sequence. For example, although this is a depletion mechanism, the free oxygens can actually combine together to raise the ozone level briefly. And you see that during these spikes during individual flare events over the course of our time series. But the net effect of many, many, many of these reactions is going to be to successfully deplete the ozone layer. So on the x-axis of our model here, we have the logarithm of the time in seconds, with the 1-year mark and the 5-year mark shown as vertical lines. And we turn off the simulation at 5 years, and so the simulation then returns to equilibrium. In reality, I highly doubt that the star turns off when we turn the simulation off, so we extrapolate a value out to try to get some estimate of how long a complete depletion would occur in our primary model, shown in black. Again, this is a modeling effort, and so there's a lot that goes into it, including how you dip from your proton distribution. So I wanted, just to be safe, to dip from the absolute bottom of the proton distribution to see if I throw as few protons as possible at this atmosphere, what's that going to do? So Matt, a colleague of mine, and I worked on this, and what he found was that if you draw from a 10 to the 5 times lower proton distribution, shown in blue, you still get 40% loss at the end of a 5-year sequence. So there's clearly a lot of work that still needs to be done to understand the particle environments of stars like Proxima Centauri. It's also worth mentioning that this is an exploratory case. We assumed an Earth-like atmosphere and asked what happens over a short time scale as you take an Earth-like atmosphere and subject it to flares like what we see on Proxima Centauri b. So taking this and proceeding with our exploratory analysis, what happens if there is no ozone remaining whatsoever when our superflare hit? Well, without that, nearly all of the UV reaches the planet's surface, and about 30 times the lethal dose for Deinococcus radiodurans is attained. That's a level of about 3.5 joules per centimeter squared that we received during our flare. If you assume no ozone, and if you assume an intact ozone column, you would get about 1/10 that level. So an obvious question at this point is, how does this compare to the environment of the early Earth? After all, we know the young sun flared a lot and was brighter in the UV than it is today, and well, we're still here. So we can try to get at that question using climate models. So I took the climate models from Sarah Ruegeimer in her 2015 paper to get at the UV fluxes on Earth during the prebiotic era and also during the early Proterozoic era. And using these models, we would expect that the UV flux on Proxima b is higher than on early Earth during the flare, but between the flare, the UV flux on Proxima b is going to be significantly lower than that for the early Earth, because M-dwarfs are inherently much fainter in the ultraviolet than our solar-type stars. And that's exactly what we find. So in the prebiotic era, our UVB flux during our superflare is about 2 times higher than that of the early Earth. And I should mention that's a diurnal average of the early Earth, as reported by Ruegeimer et al. 2015. And our UVC is 7 times higher. During the early Proterozoic, the UVB is 3 times higher, while the UVC is a whopping 1,750 times higher. So you might wonder where this difference comes from, and I can kind of illustrate that using one of Sarah's plots. So what she did is she started by modeling what an Earth-like planet atmosphere would look like in the UV at 4 different epochs in history: the prebiotic, early Proterozoic, 0.8 gigayear ago, and modern Earth atmospheres. And then she did this for a range of Earth-like planets with Earth-like atmospheres orbiting a range of spectral types, all the way from things that are earlier than the Sun into the F-star range, all the way into the late M range, as well as some specific M-dwarf stars such as GJ 1214 and others. What you see when you do this is that the quiescent flux of the sun is several orders of magnitude higher than the quiescent flux of Proxima, because Proxima is a faint M-dwarf, and M-dwarfs are just faint in the ultraviolet. However, the relative flux between the UVB and the UVC is roughly consistent in the prebiotic era at the surface of the planet. But when you move to the early Proterozoic, what winds up happening is that the UVC is suddenly a lot lower than the UVB, and so you wind up with a higher flux when you compare a given superflare energy to an early Earth. Again, the critical difference is the amount of UVC reaching the surface, and UVC is the most sensitive to trace amounts of ozone. Another point is that M-dwarf superflares like the Proxima Superflare are known to influence the evolution and continued existence of life. But how does that influence the origin of life? Recent work by Ranjan Sukrit actually shows that quiescent M-dwarfs may not emit enough UV flux for prebiotic chemistry to happen, so this may only happen during flares. To wrap up, I'd like to point out how we can take this work and extend it from just Proxima to all of the planets that are being observed by the TESS mission currently. TESS is searching the entire sky for habitable planets orbiting M-dwarf stars, and 70% of all stars are M-dwarfs, and since two-thirds of those exhibit extreme flaring and are active like Proxima, we need to understand the effects of superflares on surface life for all of these planets. So I'm working on this right now, and this is just a quick table of some of the relative information between TESS and the Evryscope. And I'll just draw your attention to these 2 points because that's a lot of information. One is whereas TESS only looks at a given star for 27 days, that means it can't observe these rare but high energy events in a statistically significant way for a given star, whereas we observe for more than 5 years. And we observe in the blue closer to the flare blackbody, which allows us to better understand the flare blackbody, especially for flares where we also have the red TESS observed at the same time, allowing us to fit a blackbody. We've seen a number of flares on test stars already, and in fact, this is actually a small sample. I have more I haven't just replotted on this graph. And we can take those and fold those into flare frequency distributions, and just like we did using the MOST satellite to get the low energy Proxima flares, we can do the exact same thing for TESS, using the TESS flares to get the low energy of our FFD, while using the rare high energy flares, getting those from our Evryscope light curves. And I've already started doing this for some test targets, and I've built average FFDs to kind of give us an idea of what we should expect as we look at individual test stars as a function of spectral type, from M2 through M5. And we find we see more superflares generally for earlier stars like M2 than we do for later stars like the M5, again, where superflare is just of 10 to the 33 or greater, whereas here 33 lies down right at the edge of our clean signal to noise. So with that, moving on towards future work, I'd like to thank my collaborators and colleagues, and I'll leave up my conclusions.
Yes, hi, you had a great talk. Oh, wow. Oh, gosh. Hi, yes, you had a great talk. I just had one question about the superflare. With the superflare, did you see or have you made any efforts toward detecting any CMEs in that flare?
Yeah, so that's actually a really good question. Because this was during the radio velocity campaign of the Pale Red Dot campaign, we actually have, did it not show up? Yeah, we actually have a HARPS high-resolution flare spectrum during the decay phase of our flare, and we did indeed search in the hydrogen alpha and several other wavelengths looking for evidence of a CME emission, and we didn't see anything, but that's not surprising because people have spent entire PhDs searching for these and haven't found them either. But we didn't see anything when we looked.
Okay, thank you.
I think there was a question. Okay, if not, I actually have a question. Boop, boop. What's the longest time series that we have in observing other stars that we could play this game for? And maybe what if that power law, for example, shifts once you go out to 30 years or 40 or 50 years?
Yeah, so that's actually a really good question. It depends on the cadence of the observations. Low cadence observations, you can go for decades, but it's also really hard to detect and really carefully observe a flare at low cadence. So if you want something with at least, say, a 10-minute cadence to get 3 epochs that are going to be above the noise, that becomes harder. And I'd say our data set is actually pretty unique in that respect because we have 2-minute cadence for about 5 years. For a given star, we can't necessarily probe the activity cycle like I think you're getting at, but what we can do is look at a lot of similar stars and look at the variation between those stars as maybe being an indicator of stellar activity, kind of mapping out that activity space lifetime.